In this video, we will be looking at rational functions and specifically how the wholes and asymptotes we see on graphs can be connected to the equations. And we're going to start with a little refresher on what we've seen on previous days. First of all, when we have wholes, it is because in your rational function, after you factored, you had a common factor in the numerator and the denominator. For example, here x plus 2 is in the top and bottom, and there might be other stuff there, but the minute you have a factor that is common on both the numerator and denominator, that will result in a whole. And the whole would be at x equals -2 here. So the restriction that you would place on that denominator for that specific factor. If it does not cancel out, whatever other factors you have in your denominator will result in vertical asymptotes. For example, if I had x plus 3 all over x minus 4 times x plus 6, there's nothing that's canceling out here, but my vertical asymptotes would be at x equals 4 and x equals -6. Of course, we can have combinations where we have wholes and vertical asymptotes. Now, for your horizontal asymptotes, your horizontal asymptote is always y equals 0 when the degree in your denominator is larger than the degree in the numerator. For example, if I had x over x plus 2, x plus 3, well, the degree in the numerator is just 1, whereas the degree in the denominator would be 2 because that is a quadratic in the denominator. So my asymptote would be y equals 0. If the degree in the numerator and denominator is the same, we would just look at the leading coefficient of the numerator and denominator. We would divide those values, and that would be your horizontal asymptote. So for example, if I had 2x minus 3 over 5x plus 6, it's the same degree, top and bottom, both 1. So I will look at those leading coefficients, 2 and 5. So my horizontal asymptote is at 2 over 5. So we're going to take this information, we're going to look at some graphs, and we're going to try to create the equations to match those graphs. Our first one, I see a whole at -2, which means I should have a factor of x plus 2 in the numerator and the denominator, because those would cancel out. I don't have a horizontal asymptote. I think I'm pretty happy with this because if I were to cancel out my two factors and simplify this, we would just have y equals 1, which is exactly what this line is. It's a horizontal line passing through 1. So this seems good to me. For B, we have a vertical asymptote at x equals 2, and that tells me I should have an x minus 2 factor in the denominator. My horizontal asymptote is at y equals 0, which tells me that the degree in the numerator should be less. Because I don't see any other vertical asymptotes or wholes, this is it for my denominator. So I can't put any x's in my numerator because the degree has to be less. So I'm just going to put 1 over x minus 2. And this relates to grade 11 because this is the base function 1 over x that's moved to the right 2, which is exactly what we see on our graph. For our next graph, we have a whole at -1, which means I need a factor in the numerator and denominator that will cancel out, and that factor will be x plus 1. I also see some zeros at -2 and 2. We haven't had that in the previous examples, so a little refresher from previous days and previous observations. The x-intercepts come from when the numerator is equal to 0. So if I have an x-intercept of -2, I should have an x plus 2 factor in the numerator And when the 0 is positive 2, I should have negative 2 as my factor. And if I were to clean this equation up, it would just be x plus 2 and x minus 2. And there we are. For our next graph, we have a parabola again, but this time we have two holes. So we have the same hole at -1, so we're going to have that factor of x plus 1 in the numerator and denominator. The other hole is at +2, so we need x minus 2, top and bottom. And although there's a hole there, the actual parabola would have a 0 there, so I do need to include it in my numerator. And then the other 0 is at -2, so x plus 2 is there. Now the reason I still have to include another x minus 2 bracket is because if I didn't, and I canceled out the x plus 1s, I canceled out the x minus 2, all I would be left with, and for my simplified rational function, is x plus 2, and in that case I would expect a line. But this is of course a parabola, and that's where this other x minus 2 bracket comes in. So our simplified version would be the x minus 2 and the x plus 2. For our final graph here, I have a hole and a vertical asymptote at 2, which is telling me I should have y equals, for the hole, I would want an x minus 1 factor in the numerator and denominator. For the vertical asymptote, I would want x minus 2. And this looks good to me because my horizontal asymptote is at y equals 0, which I would expect if the degree of the numerator is smaller, which it is. Now, in all of these functions, I wrote my equations, and for some of them I even simplified, but there is something that I did not write, which we have to go back and add on. And those are restrictions, things you did in previous years. So at the end of this equation, I'd write x cannot equal 1 or 2. For my previous one, there was a denominator of 1, x plus 1, so x cannot be -1. For the next one, x cannot equal -1 or 2 from any factors that were in the denominator. X cannot equal -2, and x cannot equal 2. Those are all the locations of holes and asymptotes. Now let's take our answer from D and E, and we're going to expand out our numerator and denominator. So for our graph in D, it was the parabola with the two holes. We had x plus 1, x minus 2, x plus 2, x minus 2, all over x plus 1 and x minus 2. And we're just going to apply our distributive property here. For the numerator, because I have 4 brackets, I'm just going to do distribution for a pair at a time. So I'll do distribution here, I'll do distribution here, and then I'll multiply those afterwards. So x squared minus 2x plus 1x would reduce to this, and then 1 times -2. For the other one, x squared minus 2x plus 2x cancels out, and then -4 all over x squared minus x minus 2. And now I'll do some distribution in the numerator to finish this off. And as a reminder, when you're doing more than just binomial times binomial, you're just taking each term and distributing it into the second bracket fully. So we're going to have x to the power of 4 minus 4x squared minus x cubed plus 4x minus 2x squared plus 8 all over that denominator from before. And let's just collect our like terms. So we have x to the power of 4 minus x cubed minus 6x squared plus 4x plus 8 all over x squared minus x minus 2. Okay, let's do the same thing for graph E. This one was a little nicer. And of course for the previous one, we would have the same restrictions as the previous graph, just -1 and 2. This one has a lot less simplifying. Okay, so I'm just doing the outsides and the insides in one step. -2x minus x is -3x. So just a little bit of distribution reminders and practice. All right, the next ones, we're going to be given information about our rational functions, and then we're going to create an equation to make it match. So write an equation for a function that is a horizontal line with a constant height of 3. So that's making me think that my rational equations should clean up and simplify to y equals 3 at some point, because it's going to be a horizontal line. But there's a hole at x equals -2. Okay, so if there's a hole, I need x plus 2 in the numerator and the denominator to cancel out. But when it cancels out, I said I wanted it to clean up to 3. So we'll add that out in front. And then I can state my restriction. And that's it. The same as part A, but this time we have holes at -2 and 5. It's going to be the exact same thing. It's just we're going to add an x minus 5 bracket to get that additional hole in there. And we'll have an extra restriction, of course. X cannot equal -2 or 5. Write an equation for a graph that has an x-intercept at x equals 1 and x equals 7. So remember, x-intercepts are in the numerator, and a hole at x equals 3, that's in the denominator. So with those x-intercepts, I would expect to have x minus 1 and x minus 7 in my numerator to give me those zeros. And if my hole is at 3, I would expect an x minus 3 factor in my numerator and denominator. That would cancel out to give me the x minus 1 and x minus 7 brackets. And my restriction is just 3 for that hole. Okay. Write an equation for a graph that looks like the parabola y equals x squared, but has holes at x equals 1 and x equals 3. Okay, well, our holes, no problem. I need an x minus 1 top and bottom to get the x equals 1 hole, and x minus 3 for the other hole. Now when this simplifies, it needs to simplify to the basic parabola. If I want that, let me just add the basic parabola in the numerator. And there it is. Just some restrictions, and we are done. Come up with an equation for a function with two vertical asymptotes at x equals -2 and x equals 5. Now for vertical asymptotes, those factors in the denominator will not cancel out. So I need x plus 2 in my denominator and x minus 5 in my denominator. It doesn't give me more information about zeros or horizontal asymptotes, so I can just be a little basic and put 1. Add my restrictions, and that's good. Okay, again, but now with vertical asymptotes at -2 and 5, but also a hole at x equals 3. Why don't you pause the video, give this question a try, and then come back to check your work. If I have those asymptotes, same denominator, but if I need that hole, the only difference is I'm going to add the x minus 3 in the numerator and denominator, plus an extra restriction of 3. Find the equation of a graph with x-intercepts at x equals 1 and 7 and a vertical asymptote at x equals 3. Pause the video, give this question a try, and come back to check your work. Okay, and here it is. Here are your zeros, 1 and 7. Here's your vertical asymptote in the denominator, positive 3, and then my restriction. The final one is the exact same thing, but we have this additional point discontinuity at x equals -5, which is just another way to say a whole. So give the video a pause, try it out, come back and check your work. Okay, so same thing as before, but I just added that x plus 5 bracket for the whole, and then I'll have that additional restriction. So there it is. From graphs or statements, we can write our rational expressions. Vertical asymptotes and wholes in the denominator, zeros up in the numerator. Horizontal asymptotes could help you figure out a potential coefficient that's somewhere out in front. Or if there was more to your graph, for example, a coordinate was given to you, then we could always add a little a value out in front and then solve for a using that extra coordinate that was given to us. And that's it.